experience. Okay, let's get going. The news of next week is there is SCCC, the leading conference in the field. Attend it. If you're graduate students, ask your advisors to send you over there if they haven't already. We will not have a lecture on Tuesday in order not to overload you. So week from today, there is no lecture. But back to our main material. What we have been studying in the previous lecture, in this lecture, is how does the technology affect circuit design. Technology is optimized for making money, for increasing the value that the lead chips make in the marketplace. So if you're an hour designer, sorry, you have been mostly thrown off the boat over here, and you need to do whatever you can with whatever is provided in technology. We've seen how is the market distributed. You know, how does, I don't want this thing beeping. So, we have seen how is the market distributed between different domains, and yeah, if they make more than half of the money off the mobile handsets, that's what technology is going to be optimized. So what we see here is many of the features that are added for the technology are optimized for increasing the standard cell density and SRAM, because those are the two biggest things that you'll find in a mobile SoC. One of the things to enhance the density is this notion that we have seen recently that layers are not created equal. Some layers, some directions are favored in order not to uniformly scale the area, but to maximize the overall scaling as reflected in design of standard cells. We'll revisit some of that. I'll mention it a little bit later today, but we'll revisit how is that going to evolve a bit in the next lecture when we talk more about the models and implications on design. Lithography restricts some things that you can do in the design, and as a if you come from old times and you had were accustomed to very liberal design rules, you find it frustrating. If you're new to it, just how it is, and you don't have to worry too much. This is what the design rules are. Essentially, what we are finding out is that lithography, people who work on lithography are really good at printing straight lines. and they can pack them as densely as lithographically possible. Make your best circuit out of straight lines. You can't. That's basically the message there. So therefore means we have restricted pitches, we have restricted orientations, and many other rules that go along with that. And there are some interesting applications and implications I'm going to be hinting on that are affecting variability. There are systematic variability effects that are caused by that have the root causes in lithography. This is something that matters because we'll be talking about parametric yields over time. And understanding the cause of parametric yield losses is something that is really important. And many of you, if you end up working on, you may end up working on a circuit that has a very high volume and a very small number of units made. Variability matters, but you can pick over there through the chips, and you don't need to reach these 90-something% yields. But if it is a high volume product, a few percent of a yield loss because of some known cause is unacceptable, and generally you will want to recover that yield loss. There are things that are over there that you will see that you will explore through harder to model correlation. We'll be hinting to some of those and some of the known mechanisms of systematic variability. And then FinFETs have more restrictions, like quantization of weights. We'll be talking more about FinFET models and design as we go along. Some other lithography implications. So we have been talking about a few implications of lithography, and we have gotten to the fourth one of them. That is those are the restricted design rules. I've hinted about them, and they're somewhat summarized over here. What we see here is a finished cell design. So this is at around 45 nanometer node. This is a standard cell back then with somewhat liberal design. This is back then what people expected the standard cell design to look like going forward. So there are a few things that you will see here. For example, around the poly was totally okay. Not completely okay, because if you take a look at here, poly line going in non-preferred direction, it was a little bigger than the one in the preferred direction. Now going down to something that looks more like 28 nanometer node or 50 node, there is no poly in the other direction. You'll find some technologies allow something like that, but it's going to be a real fast one. There are a few other things. There are these assist features. So poly design rules, poly density rules have been added. So they are much stricter over here. There is one thing that is kind of evident when looking at these two slides. Under the same scale, and this is how it was presented at in our CCC proceedings. Are they at the same scale? No. I still know if I really match the scale between the two, so I'll find out that this one was 50% bigger. The regularity costs us density. If adding regularity, people would say, is one of the reasons for losing about a half of a technology node in density scale. But we have to do it in order to get it. I mean, if you can do things more liberal, you can pack things tighter, but we can't do that. The other thing that showed up over time, and we will find still, are so-called phase-shift masks. I forgot. I said I was going to bring the mask, and this is a small enough crowd that I can bring it again on Wednesday. In a conventional mask, you have transparent and opaque features. So the light will shine through the transparent part of the mask and project something on the wafer. So there will be some kind of an electrical field that is going to the mask, and then light intensity will be projected on the wafer, and then we'll put kind of a threshold on it and project it on the wafer to make transistors polysilicon. Things that people started adding are these phase shifters, which is a different material in the mask that causes 180-degree phase shift of light. So different diffraction coefficients, and the light essentially coming out of the two phase shifters. Plus, in the mask is 180 degrees out of phase. As a result, it produces null in between and enables better resolution of features. What's the implication on the design here? So this enables scaling, but what does the designer have to do that is incredibly, if you're an analog designer, it's incredibly frustrating. As evident, say, in 28 and beyond. What does this mean? So these are two, say, polysilicon gates. So what happens? So if I have let's call it, one is a red colored polygate, and the other one we're going to call it blue colored gate. In order to keep packing them, I have to change the colors. Now I would like to add a transistor over here. Which color should it be? Or some feature over there. Assuming that I'm allowed to have that direction. Which color should it be? Because you have to alternate colors so this doesn't come out on the projection. So it has to be red, blue, red, blue, red, blue. The color above should be red or blue. If it neighbors both red and blue, it cannot be either one of those because it, well, it's the graph color. You have to alternate colors. You have to alternate phase shifts. So you end up with these rules that something that cannot be colored correctly has to be farther apart, farther away. Design rules are often confusing. You know, when you encounter that design rule error, it will refer to something coloring error. Now, you know what is going. You know, if you don't know the root cause, what is the coloring error here? Or graph coloring error, and so on. So I will not dive into that much more, but this gets more pronounced when we get down to double patterning. So in double patterning, you know, before double patterning, features in one layer will all printed in one pass by using one mask. They create one mask, shine the light on it, and make all polysilicon gates at the same time. And phase shifting enable that to continue beyond where, you know, to finer resolutions. But at some point, it was really difficult to attain desired resolutions in a single pass with a single mask. So features on the same layer, say polysilicon gates or contacts, were broken into two masks. And there are different ways how this has been done. One way of doing that is so-called double exposure, double etch. And we're going to take a look at some of those. There is double exposure, double etch, and pitch split, litho etch, litho etch. Those are two different things, and they're implemented very differently and mean different things. Some of them are completely transparent to the designer, and the designer doesn't have to worry about them. You know, sometimes you'll find a cryptic error related to that, but and then more common things that you're going to find out now are self-aligned double patterning and self-aligned quadruple patterning. So here is a double exposure, double etch approach as demonstrated on an SRAM cell down around 32 nanometer node. Look how beautiful features are in this sharp rectangle here with corresponding part. This totally, if you compare it to what has been done before, what has been done in similar nodes, this is this is what you would end up with in a single pass. So this thing has a lot of curviness in shapes. As a result, suffers from variability in the process. And then very denominator of double exposure. So how do they do that? They take the mask, one mask, polysilicon mask here for all over the chip, into two masks. One that consists of exact straight lines, and the other one of cuts. Remember, lithography people love printing straight lines. They're really good at that. And they can pack them really nicely. They don't like drawing things that designers prefer, like transistors. So they all draw straight lines and cut them. So putting those two things together, you get the rest of the so layout. You want to do one, you go more over. So double exposure, double edge is what is being done here. What was the implication of this? What's the implication to the designer? Designers mostly did not see this. The thing here is more cost. Yeah, so it costs more. To do this, they need to make two masks instead of one. There's also loss in throughput because they need to run two steps instead of one. Slows down the overall turnaround time to get the wafer back. The other double patterning, more common one, and that will give you a lot more, very similar errors and similar craft coloring errors in the design, if you are working with truly double pattern processes, is when you do pitch split double exposure. So, and that may go together with cut masks as well. So here's what they would do. You need to print a lot of dense features of the chip that beyond the resolution length, beyond these pitches that are possible with optical lithography. What they do is they split the mask into odd and even. In a similar way, how they've colored it for phase shifting. So they'll print. Let's see if I can do this here. Odd transistors in one pass, then even transistors in the other pass, and put them down together. This is also with step. One of the big things, alignment is good, but it is not perfect. And people have seen this in measured design that misalignment could have caused, sometimes causes some issues. The things that we see deployed now in FinFET processes are more like this. Self-aligned double patterning. Essentially, what they do first is we go from two lithographically defined lines like these that are completely sacrificial to making 4 pins out of that. So they will define 2 lines over there. They will deposit some kind of resist material around that. They will expose that. They move that sacrificial thing and etch into the material to define the pins. And they can keep going with it, and they can go to quadruple patterning. This is cheaper. It's a more, less masks. What's the restriction here? For a designer. Gate lengths. So these are, I mean, what we did, we just defined it. Yeah, there's a gate length over here, but that doesn't matter. You get a solo pin. Oh, you can only buy two. You buy one, get one free, whether you like it or not. I mean, you can, but it's going to be a dummy pin. There is an implication on the density and how does this translate later in some other technology nodes we may discuss a bit later. But what do you do with these pair pins that just showed up in your design? Nothing. I mean, you just turn them off. Never right there. There are things if you're, if you're doing some precision analog stuff, this will cause you again. Even in digital stuff, there are leakage paths associated with these off transistors. If the well on the other side is biased to something else, this thing will tend to leak, and it causes a lot of headaches out there. There are a good number of papers published about that, know-hows in industry, how to try to get around that. But it can surprise if you're doing something precision analog, and you really care about controlling leakage paths and stuff like that. Watch out for these dummy transistors, or just stay away from it. Okay. All right, so here is a summary of the things that we have seen so far. We have forbidden the directions that are initially introduced by the illumination type, but then added by the needs to add phase shifting and double patterning. Sometimes in some processes, polylines in other directions may exist, but they will be thicker. You'll find that there are forbidden pitches because essentially what we are doing, we're printing these interference patterns, and if we step away from that interference pattern, you don't get the desired effects. You don't get uniform things. So you'll find out that you can only, some of you are working with the say a printed process now. Some of you may be in the tape out class dealing with this Intel process. There are a few questions. Why can I have only these kind of pitches and these kind of gate lengths? You have 4 gate lengths and a few different pitches, and that's it. Because that's what they can print. That's what the interference pattern is that you get on the wafer, and you have to make the transistors up. And they're also caused by multiple patterning. There are forbidden shapes. You cannot have L shapes if otherwise you've been violating some coloring rules. And there are assist features. These assist features were hidden, or there are many hidden assist features that are added by inverse lithography or optical proximity correction, but there are some of them are now mandatory and they're visible, like dummy fins. You cannot have a solo fin. It can't print. There is no way to make a solo fin or a solo gate. So there are 2 options that are being pursued now in sub-10 nanometer nodes. One, multiple patterning with immersion, and that has had issues, right? So companies were forced to go to double patterning and somehow got through that, and everybody who had to go to quadruple patterning was slowed down. The issue of quadruple patterning, it's fairly expensive. It takes 4 times as long to do it. But what was, documented with in Intel's case were the yield losses. So Intel at their 10 nanometer node had to go to quadruple patterning in some layers, and they could not get the yields to look right. I mean, they got a lot of wafers out, a lot of things were done, but the yields were not looking right. That looked like not a good way to go. So an option in EUV lithography was developed. And we are looking at something that looks like here. How much does more? How much does the EUV cost? There was an estimate here. It was about 4. I think that number was corrected to about 3. And then, so from that point, it even will beat out quadruple patterning. So whatever needs to be quadruple patterned is going to will be voted off the island, and self-aligned double patterning will stay, and UV will replace other. Yeah.
What is that?
That's a numerical aperture that corresponds to immersion lithography. So remember, that's the n sine alpha. In air, that's maximal 1. So these are all immersion machines. Okay, so that's it for lithography and implications on the design. The idea of all what I've been talking about so far was to get you to make sense of design rules. Whenever you're designing something, I mean, we are talking mostly hypothetical, but you may want to flip through these slides once when you encounter these design rules and say, oh, yeah, that's what it is. That's what the coloring error is. When our students encountered them in 28 nanometer process, they were very frustrated with those. All right, let's talk a little bit about some of the modern processes and what are the features in there. Here's a list of things that we have, and we're going to add things at the bottom. So we'll start with shallow trench isolation, then we'll talk about the implications in the design of that, and high K metal gate, strained silicon, thin body devices, and copper interconnects. So this is the first thing that also designers need to be aware of. In particular, if you're an analog designer, you need to know this. However, it affects digital designs as well. So how do you separate transistors, say N from P or N from N? We have all seen that each transistor has A, that has source and drain regions. There's something that up to some decades ago, there was a passivation layer that was called the local oxidation on silicon, where they would just basically deposit some vapor and isolate transistors like that. That was causing this big gaps between N and P devices. If you look at all design rules, like all Revival, N to P spacing was the biggest design rule that was there. Right. Please tell me. Instead of that, nowadays, it is lithographically defined. So what happens? The bigger trench between the transistors and deposit silicon dioxide. Notice that the same process, how they intend to vary power over trails. They're going to just dig deeper with that hole there. looks good because this is lithographically defined, and it can be fairly tight. What's the issue with that trench? There may be some capacitance. Well, it'll be grounded, so that's not going to be your grounded. I mean, these things are grounded. There may be. It's mechanical. Silicon dioxide has a very different thermal expansion coefficient from silicon. So when they deposit this kind of a thing, they do it at high temperature. And then things cool down. What can go wrong with that? Well, what can go wrong is this. This thing, since it has different thermal expansion coefficients, may be bulging. So if it starts bulging into silicon, it will exert enormous pressure. Right, this is like crystal expanding. That's like the most force we can make on this platform. What could go wrong with that? An enormous pressure on silicon. Well, it affects mobility. So it changes the lattice structure. So it's that much pressure that it changes the placement of atoms in the channel here. And so what's the problem? Well, we can use that to engineer mobility. This is one of the mechanisms how the strain is introduced into transistors, into devices. So we can increase mobility by engineering that. But that's variable. It varies, on the conditions of the position. Now they control that really well. They do this like subatmospherically and so on. But also depends when you're going to have more pressure from something like this, something like that. So depending on how much of the isolation or how much of a weld space you have, there will be different performance in these devices. It affects precision designs, but also affects parametric yields in visual designs. Well, designers are very much, if you're trying to get to things to match, this is more, nowadays more important than geometric matching, pure geometric matching. High key metal gate has been introduced over time. Essentially, gate leakages, if you read the NAR paper, gate leakages as PIAs was going down were skyrocketing, and we had too much of a gate leakage. The native silicon dioxide that we had in similar devices have been replaced with high-K metal gate, and since then the leakage is pretty much gone. So we don't have to worry about that. What's the implication of design? Early on, when there used to be a replacement gate around 45 nanometers, there were implications of design. Now, none. We just enjoy it. Technology people have solved that. Strain silicon is something that we do need to be aware and affects pretty much everything, including digital design. There are two ways how the silicon, mobility is engineered in the devices. In case of PMOS devices, compressive strain helps. So something that kind of bulges into the channel compresses the channel, helps with mobility. So what they do, they implant certain germanium to affect the lattice and source the pain regions and compress the channel to increase the mobility. These numbers, 30% because of the driver, 90 nanometers were nice, they're way higher now. That unfortunately works the opposite way in NMOS devices. So compressive strain in NMOS devices reduces mobility, and that's bad. We don't want that. Tensile strain, so stretching out the channel helps mobility. So how are we going to stretch the channel? How do we do that? I mean, I know we can compress it by applying pressure. How are we going to stretch? The way what they do is they put a high stress film that drips onto materials over here and pulls it apart. Doesn't work as well. So that's why mobility enhancements don't work as well on NMOS devices, because it needs to be stretched, and we don't have a good mechanism of stretching. I mean, if you invent something like that, something that works better than this, and let us know if you can pitch. But that's the point. So this kind of compressive strain has been engineered over time. Works really well on PMOS devices, so the mobility of PMOS devices has caught up with NMOS devices. There are a few other interesting implications here. So these are the numbers that were published in 1965, and they stopped publishing them. Otherwise, they would have, I mean, if somebody finds a publication on how well does this work, nowadays we can only reverse engineer that from the transistor sizing, and we'll see that in a second. So mobility here, say 90 nanometers, improvement in mobility was through strain was 20%. On CMOS was 55%. It worked way better than 65 nanometers. 35 and 90%. And it works even better in modern processes. I mean, they really got this engineering now. So take a look at the impact on ID sat and ID left. So this is the saturation current versus the current in saturation. Can somebody tell me why 90% mobility increase only causes 50% increase in ID sat? Just like aha, or what to pay for. Exactly, velocity saturation. We plug this into the next lecture's velocity saturation equation to get the exact answer. This device is velocity saturated, so you don't get all of it. Now, in the linear currents improve a lot better. We'll see an implication of that as well. Now, a quick reminder, how do we size a transistor? How do we size a gate? And when we say in some older processes, so this is, 40 micron process from the old variation of the past image book, shows how we arrive at the sizing of 2 to 1 in an inverter. We know that back in that process, where there was no strain, people have not figured out the strain back then. We knew that mu p over mu n was roughly 3.5. So how did we end up with sizing that is optimal sizing, which is 2? The reason for that was that comes from the delay. From balancing the delay and finding what is the minimum average delay in high to low and low to high conditions. So if you take an inverter and place it in a chain, And for that chain, you're trying to minimize the delay, increasing the beta ratio or beta ratio WP over WN. Increasing the beta ratio, what does it do to TP high low, and what does it do to TP low high? Which one of these? TP high low, which of them is TP low high? So if I'm increasing the beta ratio, making PMOS transistor bigger, going in this direction, what is that going to do? It improves TP which switching direction we have, making PMOS stronger. Low to high. But what does it do to TP high to low? It makes it worse because this NMOS transistor now has to drive a bigger load. That's why it essentially linearly increases, because it's essentially a loading itself. The two intersect here at around 2.5, 2.4, but that's not the optimal. That's not where we want it to be, because it doesn't make sense to just balance TP high, TP low, TP high low, and TP low high. We want it to be here. We want to minimize them, and that minimum is around 2. That's why standard cell libraries back then were optimized for WP over WN to be equal to 1. But that corresponded to non-strained silicon. If we take a strained silicon device and plug in the numbers that correspond, we'll give you an assignment to do this. So, reverse engineer what is the mobility enhancement due to the strain. Well, when you go down to 28 nanometers, you'll find out the WP over WN is about 1.6 to 1. Because that's how the strain worked out. Yes.
Please explain how compressive channel strain increases.
The question here is, how does compressive channel strain increase its mobility? Now, I am not the world expert in solid state physics, but essentially, as it compresses the lattice structure, of the crystalline structure, the spacing of the atoms, it enhances the mobility of holes. At the same time, it makes the mobility of electrons lower. Now, if you ask me the next question, why? I don't know. I have not taken that class. But I'm sure if you take something like 230 AB, they will spend a lecture or two on that. Okay, so this is, from circuit designer point of view, totally fine. We'll take it empirically that it's 1.6. So this is quite roughly at around 28 nanometer node. Now, the next thing that has happened are thin body devices that have introduced, and many of us, and presently we have access to fully depleted SI. I'll spend a little bit of a time on fully depleted SI a little bit later in the course. But we also have FinFETs. You've heard about those, and we're going to spend a little bit more time on them. But here is something that we should watch out for, and we are going to look at a little bit more of an implication of that a little later. Remember, we've been talking about technology being optimized for standard cell bits. So standard cells come in different heights. These heights are reasonably well illustrated here. This standard cell is 7.5 tracks tall. What does that mean? That means it is 7.5 metal tracks tall. How does, what is 7.5? Where does this come from? In general, standard cells have been made to be integer number of tracks tall. That makes sense because we want to maximize the amount of routes that we can route over a standard cell. Now, FinFETs and in FinFET kind of processes, the pitches for fins are not the same as or not multiples of metal pitches are not multiples of fin pitches. The ratio between the fin pitch and the metal pitch is so-called the gear ratio. And you can come up and bring them to some kind of a least common denominator, and you'll find out that you can fit, 3 NMOS fins and 3 PMOS fins in 7.5 metal tracks. That's fine. We can live with 7.5 because the rails are shared between the neighboring cells. We'll dive a little bit more into the architecture of a standard cell a week after that. No, right after SSC, so a little more. I may not be able to fit in the next lecture. But in order to increase the density of this whole thing and take advantage of increasing ion of transistors, essentially transistors drawing in the third dimension, getting taller, the mission here is to shrink the standard cell height. So to go from 7.5 tracks to 6 tracks to 5 tracks. They're not talking about 3-track cells now in those nanowire type of transistors with buried power rates. We'll see how does that go, but it's going to be really interesting. What's the implication of if you go and look at standard cell libraries, you'll find out a whole bunch of different standard cell libraries. You'll find the choice of 7, 7.5, 9-track, 12-track libraries out there. What's the implication of those? Which one would you choose for your project? So some of them are taller, some of them are shorter. Good thinking, just the opposite. Shorter ones are more compact. So they're for higher density. Taller ones are going to be typically faster because they'll have less horizontal routing. And they use them for data paths. So some companies that build really high speed products like Intel went with very tall standard cells in the past, but most of the people are now standardizing to shorter, less metal tracks per standard cell. Essentially, taking advantage of drawing the height of fins, getting more current. Now, the strain works really well in FinFETs. Don't ask me why. Again, that's ask Ali Jarvi or Saif. Why is that the case? But essentially, it is 9 to 10. The ratio is either 9 to 10 or 10 to 11 in mobilities. In essentially ion-I-off currents, and as a result, we size them now as 1 to 1. So if you look at all the standard cells, as evidenced over here, they're all size 1 to 1. I don't see 1 to 1, 1.5, or 1.6 ratio between N's and P's. So keep that in mind. They're completely equal. The other thing, there is another technology that you may run into, and it is very popular these days, especially among RF designers. Not so much because of the performance of a transistor, but because how well it has been optimized for the metal stack for optimized for speed. This is fully depleted SR. Or extra pinch body, alternate body SR. Essentially, what has happened there is, and I mentioned this early on, is you have this buried oxide underneath the device that defines a really thin piece of silicon. It's like a FinFET, just thought that the FinFET is like this, thought it is down, back, horizontal. It doesn't scale as aggressively as FinFET, but it's out there. And the channel lengths are actually comparable to what we see in FinFETs. I'll not spend time on it now. I'll spend a bit time later. But there'll be one part of a lecture that will talk about the properties of FDSI because some of our students are designing FDSI. Now, as with the interconnect, there are two things that matter. We want in interconnect less resistance and less capacitance. So the capacitance, first speaking of the capacitance, when we talk about capacitance, we want less capacitance. So which means we want less epsilon r, which says that we need to go in the opposite direction with the choice of the oxide that we have done with the transistors. Remember, all the oxides in CMOS process were SiO2. That was beautiful. You get a native oxide to build a transistor, native oxide to build isolation. You use exact same stuff, water vapor, to isolate metal lines from each other. Now, that epsilon r of silicon dioxide is not what we wanted to start with. So for transistors, for gate materials, you want it to be higher. For isolation, we want less capacitance, and we want to drive that epsilon r down to 1. Essentially, what looks like air gap between them. So there have been quite a few of changes, but I've not seen design rule implications we need to worry about. Metallization has changed, and a long time ago it used to be aluminum that was used for wires. Now it's copper. The designers need to worry about copper. Why? Copper is softer, a lot softer than say SiO2 or whatever it is also deposited in so-called dual Damascene process, where the vias are deposited at the same time as the metal lines. But the softness adds a particular issue that designers need to worry about, which is density. There are the density rules, different kinds of density rules than what we have seen in transistors. So what you will see here is they will deposit this copper, they will bring these home, deposit copper will be bulging out, and they will grind it down to make a smooth surface such that they can deposit the next layer. As they're doing that, they're basically sanding this down. SiO2 is quartz, it's hard, copper is soft. So what we'll see, we will see some dishing over here. Depending on how much of a copper area is exposed, we'll see more or less dishing. So if you have a thinner line, it will be affected less than a lighter line. So if this line is, I don't know, 5 times, if this line over here is, say, this is a width of W, and let's say that this is a 5W, the width of this is supposed to be, if the resistance of this line is R, this one is supposed to be R over 5. But because of the distance, because some of the lines need to be removed during the mechanical polishing process. Will the resistance of this, will it be still 5 to 1? No, this one is going to have a higher resistance and they're going to be dispersed. So what are the rules that we see is that they require most of the foundries now require uniform metal densities. They used to be relatively relaxed, like 20 to 80% variation. So, metal density in a particular square in a particular region should, was supposed to be between 20% and 80%. Now they're much tighter. In some cases, they're like, they allow only variation between 40 and 60%. Very frustrating when you're trying to get your chip out, especially with an analog chip that does not like to have too much metal on your critical regions. Okay. I was talking about logic scaling and memory scaling. There are other technologies that are out there. DRAM is a huge part of the market, and it scales. It has been scaling really nicely, but it is also in trouble. There are two things that are, it's a very different process than SRAM or logic. There's a small transistor on top and a really deep trench where the capacitor is. These cell capacitors have been are getting into unsustainable aspect ratios. So that is what is challenging scaling up here. I will not dive into that. You will not see much of it. At the same time, there is an increased pressure on or demand for bandwidth out of DRAMs. We'll spend a little bit all the time on that. So there is this need for higher bandwidth to basic computer architecture stuff. Flash is also another very different technologies. It's made another different semiconductor process, and scaling of flash has been great so far, and now it is a bit challenging. The reason for that, the cell scaling has basically slowed down or stopped. Two-dimensional scaling of cells has stopped, but they're adding layers on top of each other. So essentially, what you have now are bit lines that are not going in the Y dimension, they're going in the Z dimension in multiple layers. So at the same time, they're doing stuff to the cell, making it more analog. So they're going from single layer level cell, where you're storing only binary values, now a dominant 3-bit per cell, so there is a 2-bit per cell, there is a 3-bit per cell, and they're going to 4 or 5 bits. So each cell consisting of just a single transistor is supposed to hold 32 different values. We'll see if this happens. So there are quite a few circuit technology design tricks enabled. Last 12 minutes I would like to spend on talking a bit about chiplets, because that's a very hot topic at the moment. Any questions? Okay, let's see what's up with chiplets. So one thing that I mentioned early on, something that has been persistent over the past decades is our greed for performance. And I think Professor Chen Ku has equated this to pumping oil. We know we are going to run out of oil, but we are pumping it anyway. And the same thing has been going with semiconductor technology. We have been trying to get more ion out of it. And we have been trying to get, when we could not get more ion out of the technology, we could not, we wanted to get more performance. More performance was, getting the same amount of performance increase from technology node to technology node was harder. So to get more performance, they resorted to die size increases. And this is what we have seen happening. Lately, the die sizes have been going up. What is the largest die size that you can make, that somebody can make, not us? How big is the die? Not the wafer. It is set by the lithography. It is one exposure field is 33 by 26 millimeters. And if you look at some of the NVIDIA's GPUs, they're right there, along with Xilinx's FPGAs. So this die size creep up has been there to make up for slowdown in Moore's law. What's the problem with increasing die sizes? Yeah, there are many of these leaked reports that 1 in 7 work. But these kind of things were early on are were the issues, and that doesn't work well when you are capacity limited and you're trying to make a lot of GPUs at the moment when you have to throw away half or 3/4 or 2/3 or something like that. So that's a problem. So there is a yield issue. And things get, if you're dumping that many of them, that tends to be costly. So we have seen this idea of die disaggregation. So in order to increase the yields, break up the dies into multiple modules. These are in these products, that they have multiple dies now on the package. There are the Intel's pictures. And here is a picture from Samsung showing the relative cost of going from chiplet to monolithic in the same way it goes down with the size of the silicon area that is being used, and it goes down even more aggressively with you can mix technologies and use cheaper or more mature technologies. And this goes down in 3 nanometers. This is their projection of 3 nanometers. So okay, so that's great. So how do we break our big product, our big idea into multiple chiplets? People have been looking into this for a while, and we have seen different solutions. They have all their different names over here. The challenge here is they're all point solutions. There is no unified way of doing this. Standards are open, but they have been typically deployed in only one product class. So AMD uses their own, Xilinx uses their own, NVIDIA uses their own, and Intel uses their own. If you would like to mix 2 chiplets, no way, they don't speak the same language. This is something that will need to be, there are consortia that are being formed at the moment that will try to address this. It's a pretty important thing. If you're looking for a dissertation, I'm pretty sure you can write one it'll write itself for you. It just can stay ahead of the time. Things that matter for these interfaces are the bump density and the bandwidth per edge. And what you'll find out also are startup companies that are going into this space, since these guys are trying to do, everybody's trying to do their own. Startups are, exploring the gap and trying to get in there. So the idea here is to increase the number of pins that are exposed for talking across the chiplet boundary. At the same time, you need to limit the amount of power that you can burn on transmitting state. So here is what you have in a standard package. Bump pitch is about 100 microns, and bump density is about 100 per millimeter square. Power is about 1.7 gigajoules per bit. If you go to 2D packages that you're seeing now, 2.5 is the way we call them. Bump pitches are between 36 to 55 microns. So the density increases by almost an order of magnitude as power drops down. Because you simply go to a shorter distance. And they would like to go to 3D and then undisclosed future with like 10 micron, sub 10 micron bump pitches. Things that look kind of start looking like the top metal layers. And if you can assemble things, just keep layering these dies on top of each other, it just continues. So there is a vision of the on-chip integration is going to fizzle at about 25x. Technology scaling 50x, which is, it's unclear if that is going to happen, going from now to 1 or 2 nanometers, packaging 2x, and then scale out and stack many things on top. Is Intel's vision to get to 1 billion cores per system. There is one open issue that I would like to bring up for you to think about. If you look at this Kim-Kim's plot, the plot starts at a break-even point at 150 millimeters squared. So this is when the chiplet cost is lower than the monolithic cost. This is implying that there is no hope to introduce chiplets for products that are less than 150 millimeters square. There are plenty of products that are out that are 150 millimeters square, but they're fairly expensive. What's the size of your iPhone die? Anybody has a guess? Whatever is A14, I've lost track. A14, 15, is it 15 out? So like a half of that. So it is likely that Apple would never would always stay monolithic. Things that are 150 millimeters, that's like a processor that is inside my laptop. So fairly expensive things, a few $100 each. Is there a case for chiplets? I mean, are chiplets only going to go for really high-end things? Or is there a case to make for chiplets for less expensive stuff? I think there is, but somebody will need to work on that. So chiplets for small, if you take out for small products, for small systems, if you take out the yield out of the equation, are strictly more expensive. So breaking a monolithic die into smaller dies is basically going to cost us cost of a substrate plus the cost of the interfaces on each side. What's the cost of 1 millimeter square of silicon? Well, if you take the number of millimeters square that we have on a wafer, divide the wafer cost by it, and you end up with a number that your raw silicon cost is $0.1, 10 cents per millimeter square. We exclude all engineering costs and so on. So each of these interfaces costs of the order of a dollar or so. So that's a big cost. So we are not going, it is unlikely that we are going to see chiplet solutions or chiplet breakdown into some products that are less than $50. So there are plenty of products that are in between an iPhone and a desktop that are being made in relatively low volume, where NRE is really, really expensive and is pushing them out of that market. People are trying to avoid these solutions. Now imagine something like this. If I can cheaply design a chiplet and attach it to a laptop processor, will that enable me a domain specialized solution? I think that's a possibility. All what it needs is an open interface, designed to that interface, and you get a laptop chip and a GPU and your specialized thing. It's not going to work for really cheapo things, a few tens of dollars, but if your product is $100 or $200, it might. I think we'll see that. I mean, this is inspiring me. I've had, quite a few meetings, over time with Professor Paul Gray, who is well known here. This is really bothering me. This whole world our industry used to live off making relatively low volume ASICs. There was a lot of people that are out there that were making things in, that had a volume of 10,000 or 100,000, maybe a million. Nobody wants to make an ASIC for just a volume of 1 million. It makes life difficult. This might open up possibility for sub-$1 million ASICs and a lot of business opportunities associated with that. Because FPGAs are very power hungry and expensive. All right, so that's it. So we have seen implications of FinFETs, a little bit of FDSOI on our design goals. Also, we have seen implications of lithography, and we need to kind of understand what they are. We have more interesting stuff coming. These fork sheets, buried power rails, and chiplets are going to make it a little bit more interesting again, designing things, but they'll be fun as well. In the next lecture, we are going to look again into a velocity saturated transistor and its implication on sizing transistor stacks. So try to read those papers that I've given you a couple of weeks ago if you haven't read them yet. So there is a Savini and To and Meyer. To, Ko, and Meyer. Okay. See you on Thursday.